Today we will be focusing on sketching trigonometric graphs and transforming trigonometric functions. We will mainly deal with three trigonometric functions: sine, cosine, and tangent or tan. Keep a note that we are using degrees instead of radians, so for conversion, simply multiply the given angle in degree to pi by 180. Trigonometric functions are periodic functions, which mean that they repeat their values at equal interval, which is also known as the period. For sine and cos, their periods are 360 degrees, whereas for tan it is 180 degrees. This indicates that sine and cos curves repeat the same pattern every 360 degrees, while tan curves repeat every 180 degrees. Moreover, the maximum value of sine and cos curves are 1, and the minimum value is -1. However, tan has vertical asymptotes at x is equal to 90 degrees or pi by 2 radians, which will be explained later. As a result, the range of tan function is negative infinity to positive infinity, whereas for sine and cos, it is -1 to +1. It is also called the amplitude, which is the maximum or the minimum point. However, for tan, the range is negative infinity to positive infinity, meaning that the tan function, it extends from y being negative infinity to positive infinity. Now let us move on to the transformation as well as the general sketch of the curves. There are six types of transformation we may encounter. First is the changes in amplitude. Next is reflections. Afterwards, we have phase shift or horizontal shift, then vertical shift, and then period change. Lastly, we have modulus where all negative y values are flipped to become positive y values. While sketching a curve, always write down the points where it crosses the axis, its minimum and maximum points. We already know that the maximum value of f of x is 1 and the minimum value of f of x is -1. But before that, let us find out the x-intercept. Simply set f of x equals to 0 or sin x equals to 0. So the values we get for x is -360, -180, 0, 180, and 360 degrees. Of course, we set our range of values from -360 to +360 degrees. Now let us find out the minimum and maximum points. So for that, we first set sin x equals to 1 for our maximum point. Then we will get that our basic angle of x, or acute angle, is 90 degrees. To find out the next angle this occurs at, we can simply add 360 degrees. However, we get 450 degrees, which is not within our range. Instead, we can do minus 360 degrees plus x and get minus 270 degrees, which is within our range. Now, why we do this is, as we say, the period of this curve is 360 degrees, sin x. As a result, the same point will appear every 360 degrees later. So it may be after 360 degrees or before 360 degrees. So we can do minus 360 degrees plus an angle or 360 degrees plus the angle. We can do the same for sin x equals to -1, and the values we get is -90 degrees and positive 270 degrees. Now let us sketch the actual curve. First, draw dotted lines at y equals 1 and y equals -1. This will help to draw the maximum and the minimum points. Then we sketch a wave-like curve with one point touching the y equals 1 line and the other point touching the y equals -1 line. Now we can freely label it as 91, 270, -1. Now we do the same for the negative side. It will be -90 degrees, -1, -270 degrees, +1. This is the general pattern of a sine curve, and you must always remember that a sine curve always passes through the origin. Moving on, we can express this in the form a sine bx plus d. Here, a is the amplitude of the curve, which is the maximum and minimum point. B is the period of the curve, which can be found out using the formula c/c by b. As we said, period is the angle from which the curve begins to repeat itself. C here is the phase shift or horizontal shift, and lastly D is the vertical shift. Now, this one will cover all the transformations except modulus, which is pretty simple and will be discussed at the end. Now let us look at how each of these values affect the sine function. Firstly, increasing the value of a positively or negatively increases the amplitude. So for finding the amplitude, we will always take the absolute value of a. However, negative values of a will reflect the graph at x-axis, which is our reflection part. Now, increasing the value of b has the same effect both positively and negatively. Increasing the magnitude decreases the period, and decreasing the magnitude increases the period. Just like a, which is the amplitude, negative values of b will also reflect the curve at x-axis. So we can say that minus sine x is equal to sine minus x. As for c, it will shift the curve horizontally or phase shift. Positive increase shifts the curve to the left, whereas negative increase shifts the graph to the right. As for d, it will shift the graph vertically. Positive values will shift the curve upwards, whereas negative values will shift the graph downwards. This will obviously change the minimum and maximum points. However, the amplitude will remain the same. That is, the distance between the minimum and the maximum points will be the same. It is noteworthy that A and B changes the structure of the curve, as you can see from here already, whereas C and D has no effect on the structure and only shifts the curve. Let us sketch a graph by ourselves now. Let's say we need to sketch y equals to 3 sine 3x plus 45 plus 6. Here our maximum amplitude is 3 and the maximum value of sine 3x plus 45 is 1 and the minimum value is negative 1. So we know that our positive amplitude will be 3 and our negative amplitude will be minus 3. However, we have this vertical shift of plus 6. Therefore, our maximum value or the maximum point of the function is located at a into sine 3x plus 35 maximum value, which is 1, plus d, which is 6. So the maximum point at y is equal to 9. As for the minimum point, we do the same thing. 3 into negative 1 plus 6, we get minus 3 plus 6. So our minimum point is at y equals to 3. Now let us find the period of the curve, which is 360 divided by 3 equal to 120 degrees. So each point will repeat every 120 degrees. Now this curve does not pass through origin as it is vertically shifted upwards. And the minimum point is at 3, not in a negative region. So that means it does not pass through origin and thus it has a y-intercept. So the y-intercept for this will we just put x equals to 0. So we will get y equals to 3 sine 0 plus 45 plus 6, which is approximately equal to 8.1. This is our y-intercept. And we already know that our maximum point is y equals to 9 and our minimum point equals to 3. Let us say that we are drawing this curve from minus 180 degrees x and positive 180 degrees. Now, notice this thing. We are dealing with sine 3x plus 45, not sine x. So that means this range does not apply here. So to transform the range, what we will simply do is we multiply the range with 3. So we get 3x and then we add 45 degrees. As a result, we get minus 495 as our minimum range and 585 as our upper bound. Then we find out the x coordinate of our maximum and minimum points. For our maximum points, we simply set sine 3x plus 45 is equal to 1. Then we get 3x plus 45 is equal to minus 270 degrees, 90 degrees, and 450 degrees. We achieved this by doing sine inverse 1, which gave us 90 degrees as our basic angle. Then we added 360 degrees, getting 450 degrees. And then we did minus 360 plus 90, for which we got minus 270 degrees. Ultimately, we get that x is equal to negative 105 degrees, 15 degrees, and 185 degrees. We do the same for the minimum range, which gives us sine 3x plus 45 is equal to negative 1. Therefore, 3x plus 45 will give us minus 450, minus 90, and 270 degrees. Ultimately, we get x is equal to negative 165 degrees, negative 45 degrees, and 75 degrees. Note that the curve is shifted upwards and it does not cross the x-axis. Moreover, we do not have any frame of reference. Like earlier, if it was sine x, then we'd have a frame of reference to draw a wave-like function using the x-axis, but now we cannot do it. Instead, you can do this. Add the y-coordinates of the minimum and maximum points and find their midpoint. We get 9 plus 3 is equal to 12. Divided by 2, we get 6. Now draw y equals to 6 and use this as our new x-axis just as our frame of reference to draw the curve. As you can see, the maximum and minimum points from y equals to 6 is exactly 3 units, which corresponds to our amplitude. Now we can just sketch our curve and label the maximum and minimum points. You should also note that vertical or horizontal shifts have no impact on the amplitude. The same transformation that applies to sine curves also applies to cos curves as well. In fact, sine x plus 90 degrees is equal to cos x. This indicates that cos curves is a sine curve that is phase shifted or shifted horizontally 90 degrees. As a result, sketching sine x plus 90 degrees is the same as sketching a cos curve. Let us look at the general pattern of a cos curve. Here, a cos curve starts from its maximum value, which is 1, and it has minimum points at negative 180, positive 180, basically multiples of 180 degrees, which are odd. However, it has maximum points at 0, negative 60 degrees, and a positive 60 degrees, and the maximum points are located at the odd multiples of 360 degrees. Here you can see a comparison between a sine curve and a cos curve, and sine x plus 90 degrees and cos x. You can see they overlap, so we have one curve in general. Let's see how we will deal with a cos curve transformation. As you can see from here, changing the values of a, b, c, and d has the same effect as it did on the sine curve. Changing a changes the amplitude, changing b changes the period, changing c shifts the curve left or right, while changing d shifts the curve up or down. Let's do an example. Y is equal to 2 cos 2x minus 30. Here our amplitude is 2 and negative 2. The curve repeats every 360 divided by 2, which is 180 degrees. The curve is shifted to the right by 30 degrees, as it is displayed by the negative 30 here. And there is no vertical shift, as d is equal to 0 here. Let us first find the y-intercept. We said x is equal to 0 and solve for y, which gives us approximately 1.7. Now we can sketch the curve just based on this information. So first we start from 1.7 and go up to 2, and then we go all the way to negative 2 following the pattern of a cos curve. We do this same process for the left side as well, and then we can label it later on. Let's say we are drawing for the range negative 180 degrees to positive 180 degrees. Now we need to find our x-intercepts as well as the maximum and minimum points. So for the x-intercept, we said y is equal to 0, and then we solve for x. Cos 2x minus 30 is equal to 0. So for this, we get 2x minus 30 is equal to 70 degrees, negative 90 degrees, and negative 270 degrees. Notice again, just like before, here negative 180 to positive 180 is the range of values for x, not for 2x minus 30. For 2x minus 30, it will be negative 390 to positive 330. So based on that, 270 degrees and negative 270 degrees is well within our own range. So we can say that x is equal to negative 180 degrees, negative 30 degrees, 60 degrees, and 150 degrees, and then we can level accordingly. As for the maximum and minimum points, we can simply put cos 2x minus 30 is equal to 1 for maximum amplitude, cos 2x minus 30 is equal to negative 1 for the minimum points. So our minimum points are negative 75 and positive 105, while the maximum points are 165 and 50. Thereafter, the tan curve. Here you can see how changing the values changes the shape of the tan function. Increasing the magnitude of A makes the curve more steep, and decreasing the magnitude of makes it less steep. Increasing magnitude of B decreases the period, whereas decreasing the magnitude of B increases the period. Increase in value of C shifts the curve to the left and vice versa. And as earlier, D shifts the curve upwards or downwards depending on whether it is positive or negative. Positive value shifts it up, negative value shifts it down. The period for tan curve is different. Unlike sine and cos, the period of tan is 180 degrees. Therefore, the formula to find the period of a tan curve is 180 divided by b. As we said, we follow the same general formula, which is a tan bx plus c plus d. One more important fact is that tan curves have an asymptote every odd multiples of 90 divided by b degrees. For example, for b equals to 1, our asymptote equals to 90 degrees, then 270 degrees, 450 degrees, and so on. The same applies for the negative value. It is negative 90 degree, negative 270 degrees, and negative 450 degrees. If you notice, these are all odd multiples of 90 degrees. First one is 90 multiplied by 1. Next one is 90 multiplied by 3. And then next one is 90 multiplied by 5. But here's the real question. Why does tan x have an asymptote of x equals to 90 degrees? This means that there is no value for tan 90, or it simply does not exist. The answer is simple. We know that tan x is equal to sine x divided by cos x. Now, at tan 90 degrees, it will be equal to sine 90 divided by cos 90. Sine 90 is 1, whereas cos 90 degrees is 0. 1 divided by 0 is undefined. Or to be more precise, it approaches infinity or it is infinity. So as a result, tan 90 approaches infinity, but it will never touch the asymptote itself. Let's sketch tan 2x. First, we draw the asymptotes. I suggest using rulers in this case. So we will have 4 asymptotes because 90 divided by 2 is equal to 45 degrees. So we will have 2 asymptotes with x equals to plus minus 45, and next asymptotes are 135 and negative 135. Why? Recall what I said earlier. The asymptotes are odd multiples of 90 divided by b. So the odd multiples of 45 are 45 into 3, which is equal to 135, and so on. And the same applies for negative values. Here we are drawing from the range negative 180 to positive 180. The asymptotes using a ruler. X equals to negative 135, then x equals to minus 45, then x equals to positive 45, then x equals to positive 135. Then we draw our curve and make it look like it's approaching x equals to 45 and make it very stiff as it goes up. For x equals to negative 45, it becomes very steep as it approaches x equals to negative 45. For x equals to positive 135 and negative 135 as well. Since our range is up to 180 degrees, we will not extend the curve anymore. And for the negative side, it will go down from 135 and cross the x-axis at negative 180. And for the positive side, which is on the right-hand side, it will go up to positive 180 and cross the x-axis at positive 180 and will not go beyond that since our provided range is negative 180 to positive 180. Now, how do we know that this crosses the axis at these values? For tan curves, it is very simple. You don't even have to do any calculation. The asymptotes, add them up and divide them by 2. 45 plus 135 divided by 2, you get 19. Same for the left hand side. Minus 135 plus minus 45, you get minus 180. Divide them by 2, you get 90. And for the next point where it crosses the x-axis, it is the even multiple of the first crossing. So here 90 into 1 and then 90 into 2. And the next one will be 90 into 4, which is obviously not within our range. Finally, modulus. For all trigonometric functions, this will be the same. In this case, all the negative y values are flipped and turned into positive y values. So for sin x modulus, cos x modulus, and tan x modulus, it looks like this, as shown in the image here. All the negative values have been reflected at x-axis, and all the positive values remain same. Now let us move on to the following steps you should consider while sketching a trigonometric graph. Identify the type and pattern of the graph. Is it a sine curve? Is it a cos curve? Or is it a tan curve? Then you want to identify the maximum and minimum points by including the amplitude and vertical shift. Afterwards, you want to calculate the period. Calculating the period will help us calculate the points of intersection and the maximum and the minimum points, as well as how many total waves we might get within our given range. The next thing you should consider is if there's any horizontal shift or not, which will also be included while calculating for our points of intersection and as well as minimum and maximum points. For vertical shift, always draw a new x-axis for sketching. It will be a good frame of reference and you can easily draw the curve. And finally, you should draw asymptotes for tan curves only. It is very helpful, and for this, you don't even need to calculate anything literally. You can straight up draw it and do simple calculations to find out your points of intersection. And that's all for today. Thanks for watching. If you have any further queries or wish to see more videos on trigonometry, be sure to leave a comment.